So let's look at one more easy word problem example before we step it up just a little bit as far as the level of difficulty in our word problems. So the other topic I want to address here when talking about exponential functions and word problems is compound interest. Compound interest is a situation in which we will be using an exponential function because of the idea that we're multiplying by the same value over and over and over again. The idea of compound interest is when we have interest computed on an account, that interest is put back into the account, and then the next period that comes up later, we get interest again on that new amount. That interest gets put into the account. Now we get interest upon that. And so what happens then is if we're getting interest, like let's say you get 1% interest at the end of the year. Well, if you take your interest of 0.01 and add it to the amount that you had, which was 1, then you're basically multiplying by 1.01. Then at the end of the next year, you multiply by 1.01 again, then 1.01 again, so that every year you're multiplying by the same amount. Well, the same thing could be said as far as if it wasn't every year, if it was, every month. Well, if it was every month, then instead of 1.01, we wouldn't get the full 1% since it's only a month. So we divide by however many computations there are within the year. So if it was monthly, we would divide that 0.01 by 12, because we're only getting a 12th of that interest rate. So in this formula here, the n value is the number of computations per year. So what's happening then is your a value is the total amount of money that you're going to end with. The p is your initial amount, or the amount you start with. You're going to multiply that amount you start with by 1 point something. That 1 point something comes from taking your interest rate as a decimal and dividing it by the number of computations per year. And that way we say, this is what I multiply by each computation period. Now the nt in the exponent, n is the number of computations per year, t is the number of years. If I multiply those two things together, that's the number of computations I have. So if I take the number of years that my money sits there collecting interest times the number of computations per year, that exponent is the total number of computations. So this is a formula you should be familiar with, and you should probably memorize it. That a equals p times parentheses 1 plus r over n to the nt. Now in this portion of this lesson, we're going to deal with just doing computations of this, putting it in the calculator. Later on in the unit, we'll be solving this equation and having to do a little bit of logarithms and stuff. So anyhow, I do want to point out a couple of n values that come up quite a bit. So remember, n is the number of computations per year. So if interest is biannual means every other year. So that means n is 1/2, that we get half of a computation per year. Annually, of course, means once a year, so n is 1. Semi-annually means twice every year, so n is 2. Quarterly, of course, there's 4 quarters to a whole, so there's 4 quarters to a year, so n is 4. And monthly would be n equals 12. There's 12 months to a year. Now, if we have daily interest, for the purposes of this class, for the purposes of our calculations, we're going to agree to use 365 for n. Now, I say that because there's a couple other values that can be used in other situations. If we want to be as accurate as possible for a long-term calculation, like if we want a daily interest that was compounded over 10 years, then we should probably use 365.25 to accommodate leap years. Now, the other thing that happens is there's actually a law in the United States that allows banks to use 360 for this calculation instead of 365. And really what that comes from is before calculators were super easy to use and you use tables and things like that, 360 was an easier number to use. So there actually is a law that, and this is especially true for short-term loans like payday loans, you can actually use 360 for the calculation. The moral of the story, read the fine print of whatever loan you have. So anyhow, back to our problem at hand. We're being asked to find the amount owed at the end of 5 years if $3,000 is loaned at a rate of 10% compounded quarterly. What I expect you to do in a problem like this is I expect you to write out the controlling formula, which was at the top of our page. Then I expect you to write out each of these values, each of these variables here, put a value in whichever ones you know, and then say, what am I trying to solve for? So as we read through the problem, at the end of 5 years is a time, so that's the t. $3,000 is loaned out. That's the initial amount that we got. So P is the initial amount. So that's the 3,000. The rate is 10%. Now remember that we always enter this as a decimal, so it's 0.10 or 0.1. The fact that it's compounded quarterly means n is 4. There are 4 computations per year. The A is our unknown. So if we plug these values in, we get 3,000, 1 plus 0.1 over 4, all to the 4 times 5 power. Now, if you want to do some simplifications here, you really could. I'd prefer not to. I'd prefer just to use my calculators for what they're good for. So I'm going to take my calculator here, and if I use the good scientific calculator, I have 3,000 parentheses 1 plus. I'm going to hit the fraction button, the n over d button. And that way I don't have to worry about, do I have my parentheses right and all that stuff. So I'm going to type it exactly like it appears. I'm going to hit the exponent button, where I can just do 4 times 5. Now, yeah, we know 4 times 5 is 20. You could type 20 if you wanted to. We hit enter here, and we get an answer of 4915. Now, I would round to the nearest cent, so we can see that it's going to be 85 cents. That makes the most sense. Ha! Since we're talking about money, sorry for the dad joke there. So since we're talking about money, our answer should be $4,915.85. That's how much is owed on our $3,000 loan. Now, of course, you want to stop and make sure this answer makes sense. So we started with a $3,000 loan. We're going to pay back $4,915 in the end. That seems reasonable for that very high interest rate of 10%. Now, if we end up with something like $30,000, we should probably say, oops, I made a mistake here. So in our graphing calculators or something that doesn't have the math print mode, let's talk about parentheses. So the 1 plus 0.1 over 4, no extra parentheses are necessary there, just the parentheses that we had written on paper. Where parentheses become necessary is in the exponent. We need to say in the exponent 4 times 5 is in parentheses to say all of that is in the top together. That gets us the correct answer. Now, without those parentheses there, I'm hoping that we would catch our error. That if you forgot those parentheses, that's when you get a ridiculous answer. We had a $3,000 loan that we need to pay back $16,000 on. That's ridiculous. So hopefully that's an error that you would catch and say, whoa, that's wrong. I don't want that. So catch our errors, think about whether our answers make sense.